Hello everyone, my name is Alan Ruiz. I am a nanotechnology PhD student from the University of Sonora, and today I'll be presenting my work titled Integration of Metallic Nanoparticles into 3D printed functional devices for enhanced biosensing. Biosensing is essentially converting a biochemical signal into an electrical or optical response, and over the past decades have been greatly benefited from the integration of metallic nanoparticles whose unique properties have lowered the limit of detection compared to conventional detection techniques. In this work, we propose integrating these nanomaterials into photocurable 3D printable resins to rapidly and effectively produce platforms that leverage the advantages of metallic nanoparticles for biosensing. In this first diagram, we can see the two implementation strategies that we are currently developing. In scenario A, we have a biofunctionalized 3D printed structure which has anchored biomolecules onto its surface, and it's intended to be used as a sandwich like ELISA assay using superparamagnetic iron oxide nanoparticles as probes and detecting them using a giant magnetoresistance. In scenario B, we have a thiol functionalized 3D printed structure which is suitable for immobilizing gold nanoparticles for post-functionalization, so we can use them as capable SERS platforms for detection of the analyte of interest. Now, moving to the methodology. For scenario A, we start with a photocurable resin formulation based on beta as the main monomer, VAPO as the photoinitiator, and acrylic acid as a dopant to introduce carboxyl groups into the matrix and surface. Using MSLA printing on a commercial Anycubic Photon M5S Pro, the double bonds in beta and acrylic acid undergo photopolymerization, producing 3D printed structures with exposed carboxyl groups for biomolecule attachment. Biotin was used as a model biomolecule for proof of concept, linked by a carbodiimide coupling reaction. For scenario V, we use PECDA as the main monomer and VAPO as the photoinitiator. After 3D printing, we have unreacted double bonds on the surface that can be exploited through a thiol reaction between these double bonds and thiol from a PATMP molecule to obtain a thiol functionalized surface that can bind strongly to gold. Additionally, we are including the diagrams of how are we intending to obtain both the antibody labeled gold nanoparticles and superparamagnetic iron oxide nanoparticles, but since this is an ongoing work, these results are not yet included in this presentation. Now, let's go to the results. First, we are going to discuss the scenario A, which was the anchoring of a biomolecule, in this case biotin, onto 3D printed surfaces. First, our biotin was carboxyl terminated, so we needed to perform an extra step to anchor it to the surface. In this case, we use ethylenediamine to obtain an amino functionalized surface through another carbodiimide coupling reaction. Here we can observe the 3D model we use and the actual 3D printed structure we use for all the modification steps. Due to ATR, FTIR limitations and signal overlapping, following the functionalization can be a little tricky, but we can successfully confirm it following two specific regions. First one is situated around 31 and 3600 wave number and corresponds to hydroxyl stretching. After introducing acrylic acid into the formulation, we can observe the appearance of a characteristic absorbance band situated in this region, which corresponds to the introduction of the presence of carboxyl groups onto the surfaces. Additionally, Incorporating acrylic acid reduces the intensity of the peak situated around 7020, confirming free carboxylic acid presence. After ethylene-diamine coupling, the 7020 band decreases further, consistent with the amide bond formation. And finally, after biotin coupling, we observe reinforcement of the amide 1 and amide 2 bands, along with a relative increase near 7020 from new carbonyl groups in biotin. For the thiol functional pegdad surfaces, we focus on the carbo double bond band situated around 1580 and 1680 in wave number. About 80% of the double bonds are consumed during photopolymerization, and the remainder disappear after thiolene functionalization. Additionally, a new band appears at 2500 wave number, confirming the presence of the thiol groups. Gold nanoparticles synthesized for this study had a hydrodynamic diameter of around 23 nanometers in solution. After 12 hours immersion of the thiolate surfaces in the gold nanoparticles colloid, SEM imaging revealed a uniform nanoparticle distribution, approximately 200 particles per square micrometer, covering around 12% of the surface, with an actual particle size of 12 nanometers. In conclusion, we confirm the fabrication of functional 3D printed structures and their successful post-printing functionalization. Carboxyl-bearing beta surfaces can anchor biomolecules such as biotin, making them suitable for ELISA-like assays using superparamagnetic iron oxide nanoparticles as probes. Additionally, thiol-bearing pegda surfaces can immobilize gold nanoparticles, creating potential serous active substrates. This demonstrates that functional 3D printing is a viable approach for producing biosensing platforms capable of incorporating metallic nanoparticles for enhanced detection. This is an ongoing work, and our next steps focus on synthesizing biotin-related superparamagnetic iron oxide nanoparticles and testing both ELISA-like and SERS detection systems. And finally, I'd like to thank the Bionanoengineering Group at the University of Sonora and the Materials and Processes for Micro and Nanotechnologies Group at Politecnico di Torino, and of course to Se5-P008 for my PhD scholarship support. Thank you very much.